we study quantum? It's a fair question, and I would like to address this crazy thing about physical quantities being represented by operators, this very abstract thing, matrices. I mean, why do you do that, right? And why, for instance, you talk about probabilities of events and not actual things. You don't make predictions. You don't make deterministic predictions with quantum. You're just able to say, well, there's a percentage that this will happen. There's another percentage that this would happen. This is also not at all satisfying for a physical theory. Why and how we got there. Those are just some examples of, I think, very plausible questions that I wish every single student would ask, because it's a very genuine to ask. It's not intuitive to think about the world this way. Okay? So my project, well, part of the things that I do is try to find satisfactory answers to some of these questions by going to the original sources very carefully and selecting, pieces of original sources, usually short ones, kind of 2 pages, and use them with students in order to get an idea of how some of these things were originally formulated. And I could, if, as I said, if we had more time, and maybe if you had studied a little bit more of quantum, this thing, we would then go a little bit into the details. I'll give you maybe a very broad idea, but I won't have time, and I don't think you usually need to have seen these things a little bit before in order for it to make sense. This is going to be okay, but so I'm just presenting you the idea. All right, so what I think I would say two questions that are central are so in quantum mechanics, we represent physical quantities by operators, and these operators are matrices. So the natural question that I would like to address first, but I won't go into the technical details of it, is how did that happen? When and why someone decided to represent physical quantities by matrices instead of just real numbers? I mean, physical quantities like mass, velocity, time, energy, those are numbers, right? Okay, energy is a number, time is a number. Now, why do you need to represent energy, time? Well, time is complicated in quantum mechanics, leave it out. But energy, position, velocity as matrices. So I will just present you a little bit the story. I won't go into technical details of that. So you may know that 2025, this year right now, is the celebration of 100 years of the birth of quantum mechanics. You might wonder what happened in 1925. You may have heard in the past that it was 1900 when Max Planck first came with the idea of the quantum of energy. So it's older than that. That wasn't really quantum mechanics exactly at that time. So historians agree that the birth of quantum mechanics was actually 100 years ago, and they are very precise. They point to a particular paper written by Werner Heisenberg in 1925 that marks the birth of quantum mechanics. Okay, so if someone tells you this, and you studied quantum mechanics, you want to have a look at this paper and say, well, I studied quantum, I kind of a little bit know what this is about, and I'll have a look and see how it was originally formulated. And if you do that, I promise you, you will be completely shocked by how unintelligible you cannot make any sense of that paper. I bet. I had a shock when I read it for the first time. I was like, oh my God, this is the first formulation of quantum mechanics. I cannot understand a single equation. I cannot understand a single sentence in this paper. It's crazy. So why is that, right? And so this is also a little bit the reason why I like to use some of these original sources, exactly to create that shock. Like, my God, what happened? I thought I knew quantum mechanics. This doesn't look at all like quantum mechanics. What happened in this 100 years that got us here? Anyway, so as I said, I won't be talking about the technical details of the paper. Maybe I'll give you a very broad idea. I don't think it will make sense for most of you, but that's okay. Again, that's okay. I'll leave the slides maybe for a later time. You might find it helpful. If you try to understand this paper, you probably then find it helpful. But just to make you feel at ease, one of the most prominent physicists of our time, Steven Weinberg, said he had never understood. So I will just broadly give you an idea, because I want to start from something that you probably know already. It's a Bohr model, and I come from Denmark, and Niels Bohr is also from Denmark, so we kind of like to say that this is very important. Anyway, but this is already challenging. So I'll very broadly give you an idea of what this means. You probably remember, I think you learned it even in high school, the Bohr model, right? The Bohr model is a very weird model because it talks about radiation that is emitted, like light or kinds of light that is emitted or absorbed due to transitions in energy levels of electrons, like jumping around. This is a very weird model, okay? And it was very problematic and was very controversial when he proposed it. Everyone was saying, Bohr, this is crazy. You were saying that the motion of the electron is no longer the cause of radiation. This is crazy. We learn from electrodynamics that when a charged particle is moving around, this is what makes radiation. Electromagnetic waves are result of the motion of charged particles. Now you're saying that something weird happens, that it jumps from one level to the other level, kind of is here, then suddenly it disappears from here and reappears in another level. And this jump is what causes the emission of radiation. This makes absolutely no physical sense. And it does not, and people like Einstein, like very prominent people, were criticizing Bohr for that. Okay? Well, that's another story. So one thing that it becomes a bit tricky is, like, if we want to understand how Heisenberg got to this, we need to just think, so I'll just give you a very broad idea, that but the Bohr model predicts the frequencies of, let's say, the spectral lines, but it does not predict the intensities, like how bright those lines are. And this was possible to measure experimentally. So you probably heard or seen like experiments that measure the spectral lines, which is this kind of, specific lines that described by different elements. And at the time, people could not only measure the frequencies of these lines, but also the intensity. Let's think about how bright that line is. But the Bohr model could not predict the intensity associated with these transitions. A transition is, okay, it comes from, I don't know, level 5 to level 3. It emits radiation, and that's related to a particular line. So they could predict the frequencies, they could not predict the intensities. So this is just for you to have an idea that this problem, finding the intensity of those lines, was very important for Heisenberg to come up with his theory. He was trying to find a way to calculate this. But from that is a bit of a technical argument, but maybe I think you can have an idea of the base of the argument by realizing that table right there. So these kinds of formulas, it's called Balmer formula or other sorts of formula, they allow you to calculate the frequency. Think of an emission, so it's a jump from a higher level to a lower level. You calculate the frequencies based on the levels. Okay, it comes from level 5 to level 3, you get a frequency in that formula over there. What I would like you to notice is something very interesting, that if you get low numbers like 5 to 4, 5 to 3, 5 to 2, or 5 to 1, you get a relationship between these frequencies which don't seem to make a lot of sense. But if you go to very high numbers, for instance, if you imagine that the electron is in the level 500, it's just a mathematical exercise. From 500 to 499, you get a frequency, let's call it omega. If you get a next jump, a jump between two levels now, from 500 to 498, you get 2 omega. From 500 to 497, you get 3 omega. Now there's a pattern. And this pattern is what we would call kind of harmonic series, because the frequencies, like from a jump between one level to the next one, like a one level in between, or 2 levels, 3 levels, the frequencies are integer multiples of the first frequency. And this is the structure of something called Fourier series. You may have heard of Fourier series before. So, very broadly, by looking at very philosophically deep and weird, he says the following. Every physical theory should only contain quantities that are observable, that are measurable. And the whole theory should be built in terms of these quantities. And for Heisenberg, for instance, something as simple as the position of the electron, he said, this is not an observable. Heisenberg would claim that we have been talking about electrons orbiting, trajectory of electrons, but we never observe these things. And he said, because we never observe these things, our theory shouldn't be based on these quantities, for instance, like position of the electron. So this is a radical idea, because he wants to express everything in physics in terms of the only quantities that he claims can be measured, can be observed experimentally. And those are only 2 quantities. The frequencies of the spectral lines, so they call transition frequencies because frequencies are always associated with transitions between levels, and transition intensities, which are kind of how bright those lights are, those lines are. So this is a very radical idea, and he says the theory should contain only quantities that are observable, and those are the quantities. So he says, if you want to write position, for instance, you can, but they have to be written in terms of transition frequencies and amplitudes. Okay, then this gets a bit technical. I'll give you another piece of the puzzle, which is the following. This was already known, and I don't have a blackboard, but I think you can get the idea. There's a regularity in these transitions, which is the following. Suppose you have a frequency associated with the transition from, let's say, level 5 to level 3. That's a frequency right there. And there's another frequency from level 3, suppose, to level 1. Okay, so we have a jump from 5 to 3, there's a frequency, and from 3 to 1, there's another frequency. If you calculate the jump from 5 to 1 directly, you get another frequency. This frequency is actually the result of the sum between the 2 intermediate frequencies. This is called the Ritz principle. So you will write something like this. Omega of 5 to 1, if you want to calculate the frequency from a jump from level 5 to level 1, this is equal to omega, for instance, of 5 to 3 plus 3 to 1. But it doesn't have to be 3, it can be 4. It can be, this is equal to a jump from 5 to 4 plus a jump from 4 to 1. You can make actually other intermediate states if you want. That's also fine. You can from 5 to 4, from 4 to 2, from 2 to 1. It's also so. There's a mathematical principle there. It's called the Ritz principle, and it's expressed in this equation here. Notice that K is just an intermediate state, an intermediate level. Sorry. So you start with N, you go until an intermediate level K, and then you add with the frequency from this intermediate level K to an end level M. This is equal to the frequency from the very beginning to the very end. This is something that Heisenberg wants to keep in his theory. This is an important experimental result that he needs to keep that there. So the short story, and that's just the beginning, if you're interested you have to fight with it, is that by the time he imposes this relationship, he then gets to a relationship between the intensities, which is exactly matrix multiplication. So he finds matrix multiplication as a rule in order to keep that principle there. Okay? And I see I may round up. How? All right, okay. 5 minutes, maybe 5 minutes. Now our time is up. I'm just gonna give you 5 minutes, one small lesson from Schrödinger. So I'll jump some slides, and you have these slides later. Okay. Ten minutes more, it's okay? Okay. Yeah, actually, I'm sorry. So, I'll give you, okay. So, in 5 or 10 minutes, I'll give you a story about Schrödinger. I do have a problem with the figures there, so it's not going to be, but I would like you to give you an idea of how Schrödinger got to his equation. I think it's another very fair question. Okay? And historians identify 3 different routes, 3 different origins of how Schrödinger got to his equation, or how he was motivated to come up with a wave equation for describing matter. I won't go into the details, but just this is to give you an idea that it's a complicated process. That's also why we don't use it in the teaching, because there are different routes, different origins of how Schrödinger got to his equation. I will focus on this third one here. It's a little bit technical, but I wish to give you the overall idea of it. So there's something about gas statistics that led Schrödinger to waves. There's something about theoretical spectroscopy, mainly from the work of de Broglie. But I'll focus on the third one, which is something that we no longer teach. I doubt you probably have never heard of something called Hamilton's optical mechanical analogy. But I'll give you the big picture, and I will then I'll give you the pieces for how Schrödinger got to his equation. Just conceptually, I won't go into the technical details, okay? And I think 5 or 10 minutes should be enough. So, this is a very packed slide, but let me tell you this. For this answer, I would use a series of lectures that Schrödinger wrote called 4 Lectures on Wave Mechanics. It was already 2 years after he published his work on wave mechanics. It's 1928, and I think it's the best source, it's the best pedagogical source. That's where he really explains how he got to his equation. All right, so you may have heard, and that depends on how far you got in your mechanics course. But if you haven't heard, I'll tell you about a fundamental principle of mechanics called the least action principle. Have you heard of the least action principle before? When we study mechanics, we have different ways to formulate mechanics. We often do it using forces and talk about Newton's second law and trajectory and all of that. There's a whole different formulation of mechanics called, for instance, Lagrangian mechanics or Hamiltonian mechanics. Those are different ways to formulate mechanics which are more formal and tend to be more powerful for other phenomena. It's more mathematical. And this was very well known by Schrödinger and physicists at the time, this formulations. And it's actually known today. It's very important for modern physics. Lagrangian mechanics, Hamiltonian mechanics are crucial formulations of mechanics. I would say more important than Newtonian mechanics, actually. So, but I won't get into the very details. What I'm going to tell you is that, and there are some letters here that may think complicated, but least action principle, basically, the idea is basically the following. There is some function that is minimized in the correct trajectory, and a formulation of it is a kind of a variation calculus formulation. T is kinetic energy, just so that you identify. And by playing around with kinetic energy, you get to that second equation here. Don't fight too much to understand this. Just think that M is just mass, E is energy, V is potential energy. So these other more formal, these other formulations are usually related to energy. They focus on energy. And there's a very beautiful mathematical principle. It's called least action principle. It's a stationary principle that is kind of what allows you to derive the equations of motion. So in the left-hand side, this is how, and this is from the original in the 4 lectures, like it's from Schrödinger. This is how he writes the least action principle from mechanics. Then he looks at optics. Seems a completely unrelated topic, right? Optics, and there's something in optics very powerful called the least time principle. I don't know if you've heard of that. It's usually attached to Fermat. It's called the Fermat principle. This is a very powerful principle that says light goes from A to B, and it takes the trajectory that minimizes time. So light is very smart. It always goes from one point to the other in the least time possible. You could say, well, isn't that a straight line? You say, yes, if you go with kind of, if you're moving in the same medium, that's a straight line. But then I don't know if you have heard the problem. Suppose you are at the beach and someone is drowning there, and you want to get to that person as quickly as possible, right? You probably won't go to a straight line and save her or him, right? You will probably say, you will run more in the sand because you go quickly, and then you will swim less. So then the least time path is not the straight line anymore, right? And this is just this idea that I explained to you, we can use it to derive Snell's law, because light also bends when it kind of changes from one medium to the other. It has a good analogy between the problem of the bodyguard saving someone drowning. So light is very smart. So very broadly, I would just tell you that the least time principle works for light. And what Hamilton tried to do, he tried to combine these two principles. He said, well, what if, because they look similar, what if I combine these things? And this becomes a bit technical. Again, I'll leave you with the slides. But Schrödinger made an extra step. He actually wrote energy proportional to frequency, E equals h nu, which was not something in Hamilton, but was already with Planck and Bohr, so it was already a well-known relationship. Okay, so when he combines this equation here with the left-hand side with that other one, they are both kind of relating delta of an integral, so you can combine these two things, kind of make them equal. You get to the relationship there in the middle. velocity of a light pulse in relation to energy. I'll just briefly mention this. The problem, he's trying to relate the velocity of a light pulse with the velocity of a mass point. But that doesn't seem to be possible, he says, because on your left-hand side, this is the velocity of a mass point, and on your right-hand side, that will be the velocity of a light signal. And you see, this thing here is in the numerator, and this thing here is in the denominator. So those things don't seem to be, it seems to be impossible to make them equal. Then comes something I just mentioned, that Schrödinger thinks. He says, but maybe the velocity of the mass point is not the velocity of the wave. Maybe it should be the group velocity. So I had an animation, you can Google it later because I'm just using the PDF here, but I don't know if you've heard about the concept of group velocity. It's very interesting and weird. But if you add two waves, you usually get a group of waves, and the velocity of this group is different from the velocity of the two waves. I'll just leave you with the concept group velocity, okay? So by making the velocity of the particle equal to the group velocity, then Schrödinger obtains this relationship here. And the last thing that he needs to do is put this relationship in a normal wave equation. Schrödinger wants to describe a wave. For him, wave is the deep nature of things. So he writes a wave equation. This is just a bit weird because it's P and we usually call it Y, I don't know, in V instead of U. Don't worry. But he puts that relationship into the equation and he gets what we know today as the time-independent wave equation. Okay? So I'll wrap up, and as I told you before, I'm pretty much aware that you're not following this. This is kind of maybe just making you wonder, okay, what? So, but I hope this motivates you, if you want, at some point, to understand some of the details. So I would like to leave you with this. So my last two slides. This is just a picture of what Schrödinger actually did. You know, when we study optics, distinguish between geometrical optics and wave optics. Does that make sense? Geometrical optics, we just kind of look at light rays and how they bend. Wave optics, you really kind of describe light as waves, and there's diffraction, there's interference, there's all of that. And actually, one can say that ray optics is just a simple case or a limiting case of wave optics. Like wave optics is really the nature of light. Light is really a wave, but you can make the approximation and treat light only as rays. The same thing for matter. Schrödinger is saying, no, this thing that we are describing as the motion of particles, this is just an approximate typical wave phenomena like diffraction and interference. This is the very last slide that I'll leave with you, and I hope this is just the beginning of something that you may be interested. So, if you want to follow Schrödinger's original derivation of his equation, and you might, again, be understanding now why this is not usually taught. It's very complicated stuff. I want to give you just the conceptual ideas. So first, he used this Hamilton's optical mechanical analogy, so there's something you need to understand with that. Then he makes the second jump and he writes energy as proportional to frequency. That's what he gets frequency to his equation. And the last step, he makes particle velocity equal to group velocity and not to phase velocity. And those are the three elements that allow him to get the wave equation. Okay? That was really what I had to for today. Again, I'll leave the slides, and maybe you're curious, and I now pass to you. I don't know if we have time for questions or if we have to run quickly. Thank you. Terima kasih.
Okay, give applause for Mr. Ricardo. Okay, thank you, Prof. Ricardo. Okay, and now we're going to have a discussion session or question and answer. Really.
Fine, I have time. It's just I'm happy to.
Perhaps, okay, if you have any question, please raise your hand.
You.
Okay, just one question. Okay, Oji, gini.
Good morning, Prof. Thank you for the lecture.
Good morning.
I'm sorry, actually, I don't understand too much what you explained to us,
No problem.
but I understand what you said. I'm the type of person that more like to study literature more than physics. Sorry, actually, and I really find it difficult to learn physics, especially in physics education, because I feel this is not the style that I usually study something like that, and it's really opening my eye to you explain to us about we should asking the meaning behind the Heisenberg equation and how Schrödinger get to his equation and like that. But my question is, do you have any suggestion for me to study physics differently other than the usual? Because our struggle generally, I already asked my friend and so on. We're not only afraid to answering, but we're afraid to ask, because here especially I feel people really judge us when we ask something that they don't understand or then don't like it. So we're not afraid to. We're not only afraid to answer question. We're afraid to ask question too. So maybe you have suggestion to me. Thank you, Rob.
Thank you. Thank you for the question. And yeah, I think it is a pity. I think what you're saying is sad that you say that you're not only afraid to answer, you're afraid to ask. So there's something about, there's something deep about our relationship as humans and how we perceive knowledge, that is just wrong when we are afraid to ask the questions, right? I think it's very easy to develop a way to teach physics as the physics of the certainties, and you just make the calculations. It's either right or wrong, and I mean, if you don't understand, it's just this calculation. It's all about manipulating equations and getting results, and if you're wrong, you just did something mathematically wrong on the way. I would say that that's not physics. This is just a very easy way to teach and to pretend that you understand everything and to punish your students because they don't do the calculations. But that's not understanding physics. That's not what it is. This is what we talked later about deep learning, right? Understanding physics is asking the questions. It is addressing the questions, really. It's asking the meaning and all of that. So I think you are raising a very big structural problem, right? In the way we relate, you relate with your own teachers, you relate with your own students, that has to be broken, right? Because no one is going to really learn from this model, right? So we have to understand that we don't understand, and it's totally fine to say I don't understand, but we need to be focusing on the questions, on actually asking the questions very broadly. So hey, it's easier for me to come here and say, but I know that there's a very deep, I don't know how to put it, cultural traditions. There's a lot of things that hinder that. and that we should fight against. You know, this is what we should kind of fight against, because that's not what science is. That's not what physics is. So there's one thing that maybe I could point is also what could be good materials, right? If I could mention at least one book, it's called A Cultural History of Physics, from a Hungarian author. He really writes about the historical development of almost everything that we teach in physics in a very pedagogical way. So I learned a lot these questions from that. But I think just don't give up. I mean, you are a generation, you can make a revolution, and do ask the questions. All right.
Okay, thank you, Prof. Ricardo, for the answer. Okay, is it clear? Is it clear? Okay, thank you. Okay, maybe from one person, perhaps from the female students.
We just talked about dare to ask the question.
Oh.
Yes, thank you.
Good morning, sir. My name is Nisa. May I ask you about physics? It's really hard to understand, and we doesn't know how to make it fun. And if you have an apa ya? An idea or itu. Oh yeah, do you have tips and trick to make physics more fun and
Thank you.
make it easier to understand?
Thank you. Yes.
Thank
yes.
you.
Thank you.
Give applause.
I Thank you so much for your question. I understand that, deeply understand. I think there are two levels that we can work on. I think we certainly can, and I mean, I've been here only for 2 days, but I can feel that you are very happy people. Like you like to make fun and that's great. I mean, right? This makes our life easier, and I think we should do that in physics as well. But maybe I would like to argue and stress the fun and pleasure of deep understanding. You know, so when you started your question, you seem to imply that physics is very difficult, it's very hard, therefore it's not fun, and we should make it fun. I would argue physics is very difficult, it's very hard, but it's very rewarding when you understand. And that's also where the fun should come from. You know, the pleasure of understanding. Sometimes those things take time and they take effort, but they are rewarding. So I think there are two levels. I think we should always, it's a part of the 3 pillars of deep learning, like it's joyful as one of them. I'm totally fine with joyful learning, but if it's only for fun, then, because sometimes the fun can be actually in contradiction to deep understanding. You know, when I used to teach high school, I was preparing students for exams. Sometimes I would sing some songs to them that made them memorize some equations. Oh, that's very fun. Like the teacher is singing to us and helps us memorize the equation. I would say that's not understanding. You know, so I wouldn't do that right now. You shouldn't be able to just memorize an equation. You should be able to deeply understand it. And that's where the fun for me is, and that's what we should cultivate. You know, really, it is hard work, but it will be rewarding when you understand it. And that will be a lot of fun. But it will take time, and it won't be very quick from a TikTok video and all that we were talking about. But it will be rewarding. So maybe try to convey that to your students, that there is fun in deep understanding. maybe. Yeah, thank you.
Okay, thank you, Prof. Ricardo, for the answers. Okay, maybe that's the last question because we're running out of time. Through the presentation and the question and answer session, we have grabbed the main idea. We study about equation without knowing the original, and physics is about the world, and we have new knowledge. Yeah, there's this year is the 100 years of quantum mechanics, right? And we have Schrödinger. Yeah, we have a explanation about Schrödinger and all about quantum mechanics. Thank you, Prof. Okay, before we end our agenda, perhaps we will have a documentation session. Maybe, Prof? Yeah, Prof, you can stand here and yeah. Oh, stand. You're in the center, please. You're the center. Okay. Okay, hereby we've come to the end of our agenda today. I would like to thank all of the participants, the speaker, and the committee for succeeding this event. We hope that this event will bring us to have a deeper understanding of quantum mechanics, which will be used in our academic life. It has been my pleasure to host this event. Thank you for your attention. I wish you a pleasant day and have a blessed Ramadan. Wassalamualaikum warahmatullahi wabarakatuh.